Okay, everybody. I'm going to get started with lecture 7. So this lecture is about energy and the sun. Before I really get going, I want to remind everybody that we have the observatory, the UCI Irvine Observatory, reserved tonight for this class. So this is not something you have to do, but it's kind of a cool experience. So if you're interested in going out and looking through the big telescope and taking a look at Jupiter, probably its moons, and maybe a couple nebulae, you're welcome to go out here tonight. It's between 7 and 9 p.m. We'll have Andrew Grouse, who is a Ph.D. student, who's our outreach graduate student who works at the observatory and kind of keeps things running up there. We'll be out there. I'm going to try to be out there for at least an hour or so. It's supposed to be a clear night, I think, so it'd be cool to go out. You can go on the class website, and I've linked these directions there. But just in case you want to know, the observatory is up kind of at the top of University Hills. This is the faculty housing area. So if you want to see where probably most of your professors live, you can walk through here and throw stuff at their house. Don't throw stuff at my house, it's over here, so avoid that one. So the way to get there is you come out Haltison. If you just walk straight up Gabrielino Drive, or you can drive up there. There should be, I don't expect that many cars up there this time, so it's probably okay for you to come and just find parking on the street up in here. But at the corner of Gabrielino and California Avenue right here, you'll see a dirt road. And basically you can walk along that dirt road and you'll see the observatory out there. Okay, so that's all I'll say about it. If you have any questions about logistics, you can ask me after class or shoot me an email. Any questions right now about this? Okay. If you've never looked through a big telescope at a planet or something, I strongly encourage you to do it. So there were a few questions after class last time about the discussion that we had about light, and specifically about absorption lines and emission lines. So before I jump in and start talking about what I want to say about the sun, I just wanted to give a very brief review of light and electromagnetic spectrum, just so we're on the same page. If you're starting to get really bored, you can just give me this hand signal like this. I'll know that I'm boring you. Okay. So what is light? We talked about what that was. So light is really electromagnetic radiation, and this electromagnetic radiation can come in a variety of wavelengths. So our eyes see a very small slice of the electromagnetic spectrum, but we can use lots of different kinds of detectors to figure out that there's a lot more going on in the electromagnetic spectrum besides just that little bit that we can see. The basic idea really comes from this old stuff that people like Newton used to work on, where you take normal light, visible light, and you can shine it through a prism, and that spreads it out. What you can see is that light is made up of lots of different wavelengths, and these different wavelengths have different properties. And in some sense, it's those properties that your brain interprets as color. What it really is, you can think of it as an electric field and a magnetic field that are oscillating and propagating. That's in fact what it is. And just in terms of colors, and our brain interprets colors in a very specific way. So we tend to think of objects as having a true color. And one of the things you'll see a lot of times, like in the newspaper or something, NASA will release a beautiful image of a planet or a galaxy or something like that. And you'll often hear a discussion about whether this is true color or false color. And what this really is, of course, our eyes are doing something with light. The light comes in, it's made up of different wavelengths, and we interpret that. We see things in certain ways. But when you build a detector, say, stuck on the end of a telescope, you can measure how much light's coming in very precisely at different wavelengths. So for example, you can put on a filter on your viewer so that you only see the light that's red that's coming in. And then you could basically make something like a black and white image of the light that's coming in right around the red wavelengths. Okay. So this is a picture of Saturn from right around the red wavelengths. And then you can do it again in blue, right around the blue wavelengths, and you can make another black and white, and then similarly green. Okay. Now, all this is saying is that right around blue, in this area right here, there's not much light coming in. In this area here, there's more light coming in. But all that's right around the blue color. See what I mean? So, in some sense, it's just black and white because that's just telling you bright and dark. But then you can take those three together, and then you can assign this red tint and blue tint and green tint, and then you can add them together and make a color image of it. So your brain can sort of see those three things. All right. Now, the neat thing about this then is you can take this same technique and you can apply it to wavelengths of light that your eye can't see. So for example, here's a false color composition of Saturn, but now these black and white images here are in the infrared. So this is light that your eye couldn't see, but with the detectors that you have on the end of the telescope, you can say, here's a black and white image at 2 microns, right? You could say, okay, only let 2 micron light in. My detector can tell me how much is coming in at different spots. And so then you can do the same kind of thing here. And so this shorter wavelength light is colored blue here. And you see there's more of the shorter wavelengths coming in from the poles of Saturn. But this is real because it's telling you something about the makeup of the gas, or the gas might be emitting at different temperatures, or reflecting, different types of light is reflecting differently off of Saturn. Okay. So I just thought that was kind of a nice picture, so that's why I'm showing it to you. Are there any questions about that? So the other thing we talked about light is sort of an interesting and kind of weird property of light when you first start thinking about it is you assign light these wavelengths. We know electromagnetic radiation has different wavelengths. And it turns out that the energy that the light delivers comes in single bits that are called photons. All right? And each photon has an energy that's specified by the wavelength of light it's associated with. Okay? So, and shorter wavelength light, in some sense, is made up of higher energy photons. And the relationship is exact in the sense that the energy of the photon is equal to some number times the frequency of the light. And the frequency of the light is interchangeable with the wavelength of the light. So the frequency of the light is just the speed of light divided by its wavelength. So these two things are interchangeable. And you multiply by a constant. So you can see from this equation, don't worry about what h is right now or what these numbers are. You can see, for example, that the smaller the wavelength is, that the bigger the energy is. Okay, so if you have something in the denominator that's small, the whole quantity goes up. Okay, 1 divided by 0.1 is 10. 1 divided by 0.01 is 100. So the smaller this lambda gets, the higher the energy of the photon is. And it's a 1-to-1 relationship. Okay, so what you can see from this already is very long wavelength stuff, very long wavelength radiation is going to have low energy photons, and I mentioned this before. The long wavelength stuff is like radio waves. And the short wavelength electromagnetic radiation is, for example, gamma rays. So gamma rays are made up of very energetic, powerful photons that you don't want hitting your DNA and breaking it apart, for example. The specific value of this H is, in these specific units, 6.6 times 10 to the minus 34 joules times seconds. So it has units of energy times second. And that allows it to have units of energy when you multiply it by a frequency. Because frequency has units of per second. Okay. Now, the specific unit of energy, joule, is something that I'm going to return to later in the lecture and just talk about exactly what energy is. So what am I talking about when I talk about energy? Are there any questions about this?
What did you say, H nu?
So nu is the frequency of the light, and H is called Planck's constant. It's just a constant. It's as far as we can tell, it's a fundamental constant of nature. Any other questions? So this is just one of these charts, I think I've shown you this one before, that sort of summarizes the electromagnetic spectrum and different properties. So we have long wavelength stuff, we have short wavelength stuff over here. So the short wavelength on this side of the diagram, the shorter wavelength, higher frequency of light, stuff like X-rays and gamma rays. Visible is in the middle here, and the radio waves are at the longer wavelength or the lower frequency. Down here, if you recall, depending on the temperature of an object, it'll glow a different color. That's called black body radiation. So if you have a hotter object, it spits out its photons at higher energies. And these are just the temperature scales associated with these different wavelengths of emission. So 10 million degree gas is going to glow in the X-ray, whereas very cool gas, cold gas, will glow in the radio. And again, I mentioned this just now, this high frequency, short wavelength electromagnetic radiation is associated with high energy photons. And then over here, on this side of the diagram, this light's going to have very low energy photons. Yeah?
Is it true that the more higher energy photons are
So you said, is it true that the higher energy photons are more harmful to you?
Yeah.
Yeah, generally, yes. Right.
And like microwaves, is that like too?
Well, okay, so you're saying, well, then what about microwaves? Well, you know, more or less, microwaves are a lot better for you than X-rays. Okay. Now, there's more subtle effects that you might worry about with microwaves, and this is things that, so for example, you know, microwaves are built, some microwaves are built so that they excite water and make water boil. Okay, they're built with just the right frequencies that they excite water and make it want to move around and boil. So you don't want to stick your head in a microwave and turn it on or whatever. With water in your head will boil. You don't want that. So you know, there are subtleties. You know, you can design things that. But more generally, I mean, basically though, if you were going to be hit by just a little bit of microwave radiation that's going to come at you versus X-ray radiation, I would vote, if I had the choice, I would vote microwave. Okay. And again, radio waves, we've got radio waves going through us all the time.
Are those harmful too?
Most very long wavelength waves are not, and it's sort of debated as to whether the kind of wavelength rays that are associated with cell phones may or may not be harmful. Yeah, I'm not an expert on that, though. Yeah.
I was going to ask you a question about that.
We could talk about it after class. They're recording this, so whatever random thing I make up, I might get sued for. And I'm not scared of saying what I believe, but if I just make something up, I'm a little scared about that. Okay, so the other thing that we have to think about in terms of this light is, you know, the reason why I'm really talking about light is I want to use the light to study things that are outside the Earth. And when that light comes to hit the Earth, it doesn't always get through the atmosphere. All right? So in fact, our atmosphere has very specific windows that allow certain types of light in, certain types of electromagnetic radiation in, and other types of electromagnetic radiation does not get to the ground. And basically, that's because the atmosphere tends to block out a lot of the electromagnetic spectrum. Okay? So, for example, you know, the visible light, most of it makes it to the ground. What's plotted on the top here is the opacity of the atmosphere. So what that's saying is, if it's 100% opacity, it's 100% opaque. So it doesn't get through to the ground. Whereas if you have a very low opacity, then a lot of the light gets through. So you can see that it's very low opacity around the visible light, around here. And then as you get to, you know, there's this kind of area right here in the IR, the infrared, where the light doesn't get through. And then there's this big fat window in the radio, which is open. So radio waves hit the ground nicely, and so we can take radio telescopes, for example, and point them up and study radio waves coming from space. And then the very longest radio waves are blocked. Similarly, gamma rays and X-rays are primarily blocked. So you might ask yourself, so why does this matter? So one thing that this tells you right away is that if you want to study light or electromagnetic radiation that's not in these very specific bands, if you want to study that light coming from astronomical objects, you need to get up above the atmosphere as much as you can to see that light. And that's one of the primary reasons why we put telescopes in space, or we put telescopes on airplanes or on balloons or rockets, is to get it up high so then you can actually detect this stuff before it gets absorbed by the atmosphere. All right? But you might ask yourself, what's going on with the atmosphere? What is happening in the atmosphere that's blocking this stuff? And you'll notice that like what's up with this? You know, it's not like it's a broad, just sort of smooth transition. There are these kind of peaks where the opacity goes way up. That is, where the atmosphere absorbs stuff in very specific regions in this diagram. And then in regions right next to it, it lets stuff through. So what's going on with that? Well, that's basically a characteristic of absorption lines. So that's this idea that we talked about last time, that if you have material, like atoms and molecules, that material will have kind of its favorite kind of photons that it wants to absorb. And it can be very discrete. That is, there can be very specific wavelengths where a certain type of material will really want to absorb that stuff, and at other wavelengths it will just let it through. Does that make sense? So for example, over here in the gamma ray and the X-ray, that's primarily being absorbed by oxygen, molecular oxygen, and ozone. That's for the ozone layer we'll talk about. And then these lines here are water vapor absorption, and in some cases CO2 absorption. So carbon dioxide will block some of this stuff, and water vapor blocks some of this stuff. And then there's this big gap. And then over here, this is just basically broad reflection of the waves off of the Earth, off of the ionosphere, just stuff coming in and just bouncing off, as opposed to being absorbed. Yeah.
People say like our ozone's being damaged and the atmosphere's being damaged. Let's say that ozone's being damaged. Does that mean like things won't get absorbed after a while?
Yeah. Right. So one of the fears with ozone depletion is if you get rid of the ozone layer, then you have more harmful UV coming in, giving everybody cancer and stuff. So you don't want that. Hurting animal life and things like that. So, with this general feature that you have certain types of molecules and certain types of let's think about it even more simply, certain types of atoms like to absorb different types of light, is an interesting phenomenon that in fact we can use to learn things, right? So in fact, if you understood this chemistry very well and the nature of absorption very well, you can use this to figure out what the atmosphere is made of, right? And this is why we know there's carbon dioxide and water vapor in the atmosphere, among other things, right? I mean, obviously we know there's water vapor in the atmosphere. But more generally, you can use this general idea to study the composition of things that are then far away from us, out there at astronomical distances. And so the idea is that, you know, if you have a star and that light shines into a telescope, it wouldn't be this kind of telescope, with some kind of spectrograph on it. You can use that to figure out what stuff is made of. So spectroscopy specifically it's the practice of using light, spreading light out, and understanding it and looking at the constituents of the source to figure out what they're made of. So, and I'm going to talk a bit about this now. So, let's think of a very simple circumstance. Now, imagine that we're looking at a black body. Okay, remember this idea of black body. Black bodies are things that shine with just a distribution of wavelengths, a distribution of colors that depends only on the temperature. Okay, and that's it. It's a smooth distribution of colors coming out. So if you had light that was, say, a white light source that didn't have anything else in it, that didn't have any characteristics other than just emitting this light, you send that light through a spectroscope or something that spreads the light out into its constituent wavelengths like a fancy prism, and then the resulting spectrum you would see would look like this. It would be continuous. It would just be this smooth thing. But now imagine that instead of this sort of perfect source, you instead had some kind of gas, okay? Like say it was helium. And you heated up the helium, and then you get that light and shine it, okay? Now, if it was a very specific type of helium, like pure helium that was just shining, most of the light you would see would be in characteristic lines. Okay, so that had very specific wavelengths, or in this case, very specific colors. And the values of those wavelengths, exactly what colors they were, would tell you what kind of gas it was. So you might look at this and say, oh, okay, that's got the signature of helium. Or if these were, different lines and moving around a little bit, you say, oh, okay, that's hydrogen, that's not helium, or that's neon. Okay, that's the basic idea. And another thing that you can do with this, imagine instead you had this perfect white light source, but then before it gets to our spectroscope, so we can study it, you instead stick a ball of cold gas there that wasn't shining on its own. That gas will absorb some of the light, but the kind of light that it will absorb will be very specific. It'll absorb only the wavelengths that it likes. And the wavelengths that it likes are determined by the kind of gas that it is. So helium likes specific wavelengths, and it might be these three right here. And so then when you look at this spectrum, you'll see dark lines where these bright lines were, because it's absorbing that light. Okay? And then you can imagine using this to then learn what this gas is made of, or what this glowing gas was made of. Does that make sense? Okay.
What happens to the photons when they're absorbed?
They get spit out again. They'll get spit out again. But rather than being spit out, the thing about it is, they get spit out in all directions. Okay? So the light coming in this way, a bunch of it gets absorbed. Right? And then you wait a little while, and those atoms will spit that light back out. And that light will actually have the same wavelengths usually as the ones that are absorbed. Or in many cases they will. But it won't all go in this direction, it'll go in every which way. So there's a net deficit in stuff that's coming this way. But if you had a telescope over here, and were watching it, you would see emission lines that look just like this. That's the light it spits out. Does that make sense? It's a good question, yeah.
So when you're looking at like a white light and you get a resulting spectrum, your spectrum could vary. The white light's like your spectrum could have multiple ones.
Yeah, exactly. So yeah, his question was, but if you're looking at it from this white light, this could be, depending on the temperature of this thing that's called white light, your spectrum could have more blue or more red or more infrared or whatever. That's definitely right. But the important thing is it's smooth. And it doesn't have little dark lines or bright lines in it. And it's those lines that we care the most about when you're trying to do spectroscopy, when you're trying to understand what things are made of. Okay. Now the other thing that you can do here, right, is if the thing you're looking at is also moving, that will cause a Doppler shift. Who remembers what the Doppler shift is? Someone remind me what the Doppler shift is. You can use it with sound too. What's Doppler shift? Someone remember? Yeah, it's like with the police, like when something goes meow. Okay, it's the idea that the pitch will drop as something recedes away from you. That's the general idea of Doppler shift. But you get the same thing in light. Okay, and then with light, it's called redshift. So when something's moving away from you, all the wavelengths of the light will be stretched out in the direction away from you. So the light, if it's emitted, say, imagine you have light that's emitted that's pure blue. If the thing's moving away from you at a fast enough speed, it'll get stretched out, so now it looks, for example, red. And there's a precise relationship between how fast the thing is moving and how much the light will get stretched out. Vice versa, if the thing's coming towards you, the light will be blue shifted or scrunched. And so then the wavelength shift will move depending on whether the thing's moving away from you or towards you. Okay? So imagine you see these lines, okay? This is the lines that you would see. Like this is just, see, pretend this is helium, right? Oh, this is helium, I can tell, I know what helium looks like. Now, the star, if instead that same star is moving away from you, you'll see something that looks like helium, except everything's displaced. And you'll say, oh, it looks like helium, except it's all shifted towards the red. Oh, that thing must be moving away from us. Or vice versa, it looks like helium, except everything's shifted towards the blue. So that thing must be moving towards us. So not only have you learned what this thing is made of, but you've learned how fast it's moving and which direction it's headed, either towards you or away from you. Does that make sense? Yeah.
That's similar to a kitchen stove, like how it's blue on the bottom and red on the top.
Is that like a kitchen stove where it's blue on the bottom and red on the top? Not really. On a kitchen stove, the reason why it's bluer on the bottom is because it's hotter on the bottom. The speeds we're talking about are really fast, like near the speed of light to see the effect. So nothing you would see, like you can't argue your way out of like a speeding ticket because you thought the light was actually green and really it had redshifted, because you'd have to be going way faster than the speed of light. Or not faster than the speed of light, but approaching the speed of light. I don't even know if it goes in the right direction. Okay. So how does this absorption work? Okay. So let me remind you. So it depends. So you have to think a bit about what an atom is in order to get this right. So remember what an atom is. An atom has a nucleus, and in the nucleus there's neutrons and protons. So the nucleus is positively charged, and there can be neutrons and protons there. And the thing that tells you what kind of atom it is, I'll come back to this later, is the number of protons. Okay. It doesn't really matter for our discussion right now. You have a nucleus, it's sitting there, it doesn't really matter for this discussion, it's there. The thing that matters is there are these electrons going around it. And if you have a neutral atom, you have the same number of electrons as you have protons. Okay? So imagine you have a really simple, this is just a cartoon, imagine you have a really simple atom. So this is something like hydrogen. You've got a proton, you've got a single electron. Under most circumstances, hydrogen is going to be sitting in what's called the ground state. Okay? That means the electron is sitting at the lowest energy level. So it's sort of at this, has specific energy that's associated, you can think of, with orbiting near the nucleus. All right? Now, if that electron gains a specific amount of energy, but only a precise amount of energy, what I'll call dE, it can move from this ground state to what's called the first excited state, or an excited state. But it can only do this if it gains an exact amount of energy that's associated with this jump. There's no in between. Okay, it can either be in this state or this state and nowhere in between. That's one of the mysteries of quantum mechanics. Okay? So is that, you know what I mean by that? Who's seen this kind of thing before? Who has not seen this kind of thing before? Okay, so good. So I'm glad I'm going through it. And those of you who've seen it before, you know, just take a nap or something for a second. So, but the important thing here is that the amount of energy difference between where this electron sits and where it can go in the excited state depends on the type of atom it is. Because you can imagine as you put more protons here and you change the type of atom, it is going to be a different amount of energy to jump. So it's going to change the configuration, it's going to change the type of atom you've got. Similarly, there might be another excited state out here, and that could be a different energy. And that would correspond to one of these different lines, as I'll talk about in a second. So, what I'm talking about then is, imagine you have an electron. You have an atom with a nucleus and an electron. This is the ground state, and this is an excited state. The blue thing is the excited state. This is this normal atom. But then a photon comes along, and that photon happens to have the exact amount of energy that this atom requires to jump from the ground state to this first excited state. So it absorbs that. It takes it and uses that energy to jump up here. So that's what's happening to the atoms when they're absorbing these specific lines. They're getting excited. But the important point here is that not all light, not all photons can be absorbed this way, because you need to have that exact energy to jump you up to the excited state. If you're a little bit off from it, it's not going to absorb. be either a little higher or a little too low. It doesn't matter. It's not going to absorb it. It's only that very special light that each atom likes. Only those photons that match up with the allowed energy levels can do this. So only photons of specific energy or wavelength can be absorbed, and that specific energy or wavelength depends on the atom that's doing the absorption. And so if you have continuous light shining through a blob of atoms, the lines that will get absorbed depend on the nature of the atom because of this structure. Does that make sense? Question about that? Similarly, now imagine you have an atom that's been excited. Okay? One way or another, it's been excited, it's sitting up in this state. What tends to happen is it wants to fall back down to ground. Eventually, it's going to fall back down to ground because that's where it wants to be. Now, when it does so, it has to give up energy by energy conservation. And when it does that, the energy that it gives up will be in terms of a photon. And that photon will have the energy that is associated with this energy difference here. So it spits out a photon of a specific energy, and therefore it has a specific wavelength. And it will look like a single color in the spectrum. So just as only specific light can be absorbed, only specific light can be emitted. So it's basically the same fingerprint. You either see the fingerprint in absorption or emission, but it's basically the same fingerprint. All right. So these are just some examples. This is what hydrogen looks like: helium, lithium, oxygen. And they also can have signatures that are beyond the optical bands, so that your eyes can't see. I'm just showing you the ones that your eyes can see here. And, you know, for your purposes, it's just that this is known. We know what these are. You can do these in the laboratory, you can make these measurements, and we know exactly what it looks like. And then you can use it to learn about what things are made of. And I think I mentioned this in a previous lecture. Helium, this one, was actually discovered by looking at the spectrum of the sun. Helium was discovered in the sun before it was ever discovered on Earth, using this type of technique. That's why it's called helios. Yeah.
Is there a way, I know this is about the stars, but is there a way you can do spectroscopy on like things on Earth?
Yeah. People do spectroscopy of things on Earth all the time. And it's exact, people do it. But there's whole fields of that. It's not something the stars, it's things on Earth.
You know, like little like glasses or goggles or
Anything, yeah. There people do it for all different types of spectroscopy on Earth. You know, understanding plants, you know, all kinds of stuff. Yeah, good question. Yeah, it's a very broad technology. Yeah.
So this is what the atoms look like before they lose their energy and fall out.
This is like if you take a whole conglomerate of atoms and you excite them in all which way you can, and then let them, and then they just start spitting out light. This is the light. These are all the different types of light that they spit out. Sometimes it's their like the 9th excited state, and then they decay down to the ground state. Sometimes it's like the 4th excited state, decay down to the 3rd excited state. So there's all different. That's why there's so many lines. There's so many different possibilities of changing states with those electrons. And more generally, the more complicated the atom is, you know, the crazier the lines get. And actually, at some point, I think I mentioned this last time, that the atoms get so complicated that you can't actually solve the equations for what the light should look like. You just have to do it experimentally. And in fact, I'll say this too, that quantum mechanics was one of the reasons why quantum mechanics was invented was to explain this. This is weird. No one could understand why this was like this. Okay. Yeah.
So the initial lines will change whenever the atoms change energy level?
Each type of energy level change is responsible for a different line. See what I mean? So this line might be for the 2nd excited state to the ground state. This line might be from the 3rd excited state to the 2nd excited state, etc. So there's all different ones. think I did it the wrong way. These are higher energy. You're losing more energy in your transition as you go this way because these are shorter wavelengths. And you're losing less energy in your transition as you go this way because these are lower energy photons. But there's just lots and lots of different possibilities there. Okay. So if you take in all those like orbitals, people who've taken chemistry with like all the orbitals that you have to remember, who's done all that? How many people have taken that stuff? All those possibilities, right? These are all different lines. If you haven't taken that, don't worry about it. The only thing I want you to get out of this is you can use the emission or absorption as fingerprints to tell you what type of atom they are. So now I've been talking about these energies of these photons. Okay, these photons have different energies, and it takes different energies to excite atoms. But I kind of have been using the term energy without defining it. So, since no one stopped me, everyone must know exactly what energy is. So, what is energy? Help me out. Yes?
Mass times the speed of light.
Mass times the speed of light. You're close. Mass times the speed of light squared. Close. Close. But yeah, that's what you mean. Okay. In more everyday terms, please. I'll get to that too. Yeah. Yeah. Like heat? Yeah, I mean, you could store energy in heat, yeah, right? So we're getting examples of what's another kind of energy. There's energy in like a moving fastball. Kinetic energy, right? So that's a kind of energy, kinetic energy. So something that's moving with mass has energy, that's called kinetic energy. Is there a broader definition? Okay, so the way we define energy in physics is the capacity to do work. Okay, so energy is somehow, it can be in lots of different forms, it's somehow storing or containing the ability to do some work, right? And then you might ask me, all right, well, what's work? So work is defined to be the force applied through a distance, okay? So if you pick up something up over your head, you do more work, twice as much work, if you pick that thing up to twice the height. You have to apply a force to pick it up, and if you apply the force through twice the distance, you've done twice the amount of work. In order for you to do that work, you've had to expend some energy. And how do we get our energy? Sorry? We eat, right. So you eat. Our bodies magically somehow take that Twinkie and turn it into the ability to lift things up over our heads. Right? Actually, maybe there are no more Twinkies. Is that right? Right? I'm sure there'll be Twinkies. Don't worry. Don't worry. Now, so it turns out actually that this word energy is a fairly new word. But in the mid-19th century, it became to be realized that this idea of energy was a pretty powerful thing, and that many different processes could be used to explain energy being transferred from one form to another. So for example, in a steam train, you have coal, which you burn. You burn the coal, and then that makes water boil. The boiling water releases steam. The steam rises, turns a piston, gets a piston moving. That's attached to a wheel, and that makes your train go. So somehow you've taken the chemical energy that was locked up in this coal, and you've turned it into kinetic energy of the train. You've let this chemical energy in the coal do work on the train, and the train is now moving. So you're pushing that train along using this type of energy. But the point is that the energy is conserved. If you could keep track of all the minute detail of how much energy, how much chemical energy was in the coal, how much of that was released when you burned it, how much of it was wasted by kicking off soot and in thermal, and heating up things around it, and how much actually went into making that water boil, etc. If you could count up all the amount of energy that was released when you burned that coal, it would be conserved. There's no energy created or destroyed. You're just moving it around from one kind to the next. And so that's this idea of energy, and it's powerful because you can apply it to lots of different things. So in much the same way, our bodies take the food and somehow get chemical energy from it. We eat up that carbon, and that carbon is used in our bodies to do things. Now, we have different units for how we characterize energy. So a familiar unit is the calorie. So the calorie for a physicist is the amount of energy it takes to raise 1 gram of water, about a thimbleful of water, 1 degree Celsius. That's how you define a calorie. So you take a little thimble, you raise the water, you raise it by 1 degree, and that amount of energy is a calorie. Now the calorie we talk about with food, that's actually a kilocalorie. Okay, so that's 1,000 of these calories. So if you had 500 food calories, like a Big Mac, if you could take all of those food calories and turn it into just heating up water, that's actually about 500,000 calories of energy. So that's how much energy it would take to raise 500,000 grams of water, 1 degree Celsius. At some level, when it's cold outside, that's what your calories do. They keep your body from being too cold too. They heat you up. So you can eat more when it's cold. Now another common energy unit that you'll see is a joule. This was the thing I mentioned before. A joule is equal to about 0.24 calories, or put it another way, a food calorie is about 4,000 joules. I'm just giving you some units. If you have never seen this before, I just thought I would mention this. So for example, lifting 100 pounds over your head takes about 1,000 joules of energy. Turns out that's not even 1 food calorie worth of energy. Now, where do we get all this food? Where does the energy, remember how I said remember I said energy, all it's doing is being transformed from one kind to the next. So this food that we eat, where does that energy come from? What is that energy? Where did the energy from the food come from? Yeah?
Sun.
The sun, thank you. Wow, good. What do you mean by that?
Well, anything that grows, we get from the sun.
Yeah.
And most of the things that we feed animals with grow from the sun.
Right, exactly, right. So, even if you're eating animals, right, those animals are ultimately eating plants. And those plants get their energy from the sun. So the sun, and in fact, even if we're burning oil to cook our food, where does the oil get its energy? The oil is just like old plant matter and dinosaurs and stuff, right? Where's that energy? Where do they get their energy? From the sun, right? So all that energy, almost all the energy we use, is ultimately coming from the sun. So the sun is very important, obviously, right? It provides that energy source. Ultimately, it provides a very important energy source. Almost all the energy we use is ultimately coming from the sun. Now, that's not true of nuclear power, and some geothermal power and small power sources like that. But all in all, the sun is really important for our energy. And it has been important for our energy. So photosynthesis, the process by which life uses this energy from the sun, it turns out it's actually trapping only a tiny, tiny fraction of the amount of energy that's hitting the Earth from the sun. It's only like 0.1% of the energy that reaches the surface of the Earth is actually being used up by a photosynthesis. A big, big chunk of the sun's energy is actually being reflected off by clouds and ice. And it's kind of a weird thing that the more ice you build up on the Earth, the more of the sun's energy is going to be reflected back. But the rest of this heat goes to basically heat the land and the water. And it turns out in this cycle, to keep the Earth warm, that tiny, tiny fraction of carbon dioxide in the atmosphere is really important for that. The Earth's about 35 degrees warmer than it would be otherwise if you got rid of all that carbon dioxide. That carbon dioxide it's not very much of the atmosphere, it turns out. Now, think about this for a bit. Like I just said, all of the energy on Earth, all of this energy that we use is all coming from the sun. Now, that's kind of amazing if you think about it, because think about how far away we are from the sun. The sun, it's not like the sun is like a laser beam and is pointing all of the energy that it's got just right at the Earth to make sure we're happy, right? The sun is just spitting its energy out in every which way. And that tiny, tiny fraction of the energy that it's spitting out that we happen to intersect because we're there is what we're living off of. And in fact, yeah.
When you say that the energy, one-third is of energy affected by the sun's class, are you talking about the albedo effect, or are you talking about that in the third when you're saying the rest was that?
I'm just saying that, yeah, I'm talking about albedo, just a third of it's being reflected back. Well, no, the land is basically heated by, some of it's just being absorbed and re-radiated, right? And some of that heat then comes back as being absorbed by carbon dioxide. But there is some that's actually just being reflected off of the clouds. It just like comes in and bounces right back. Now some of it in that process is absorbed, but a lot of it's just like reflected, just like a mirror reflects light. A good chunk of the light is actually just reflected. It just goes back out. Yeah.
Over time, is the sun like giving off less, very small amounts, less energy? It doesn't have an energy source itself.
Well, the sun does have an energy source, and that's where I'm going. Okay. The sun does have an energy source, and the evolution of the sun's temperature is another lecture. But the sun definitely has an energy source, and that's where I'm going. I'm setting you up. I'm trying to set up for that. So, where I was going before this, though, was just talking about how much crazy amount of energy the sun is spitting out. Because all this energy that we're collecting, okay, that we power everything with, which again is only, all the photosynthesis is only 0.1% of that, is being collected by this tiny dot compared to the sun. See how small it is? Right? But this is not where the Earth is, fortunately. Okay? The Earth is 150 million kilometers away. And the sun is spitting its energy out in all directions at that radius. So imagine a little sphere of energy that's being spit out around the sun. That same group of photons is spreading out, spreading out, spreading out for 150 million kilometers. Until finally a little bit of it intersects the Earth. And a third of that's reflected off. 2/3 of that's eventually taken care of, absorbed. The Earth gets only about 2 billionths of the sun's energy at any given time. So what this means is, there's a lot of energy coming out of the sun. A lot of it. Huge amounts compared to what we're used to thinking about. I tried to come up with a little analytical calculation so we could see how much energy it was, but this doesn't make any sense, but I thought I would do it anyway. It turns out that the luminosity of the sun is 10 to the 26 calories per second. The calorie unit that I talked about before, lowercase c. Luminosity is energy per second coming out of the sun, 10 to the 26 calories per second. The sun's luminosity, if you put it in terms of Big Mac calories, is the equivalent of 2 times 10 to the 20 Big Macs per second. I have no idea what that means. But I just thought it was so weird that I would show it. Okay, wow, everyone's like, yeah, that's a lot. So yeah, so it's a lot of energy. Now, we are not the first people to realize that this is a lot of energy. And there's an interesting story. So what physicists began to think about then, as they began to understand what energy was, And as you can take measure of how much energy is coming out of the sun, right? You can measure this. People start to wonder, well, where's this coming from? How can the sun have that much energy? What is the source of energy in the sun? There's this interesting story of a debate that actually happened between a very famous physicist at the time, Lord Kelvin, and Charles Darwin. So this sets the time frame for you. Okay. Lord Kelvin, it's the same guy that the Kelvin temperature scale is named after. Okay. Probably the most respected physicist alive at this time. And Kelvin had thought about the sun, and specifically he wondered how old the sun was and therefore how old the earth is. Now at this time, the most powerful source of energy that anybody knew about in physics was gravitational energy. And you can figure out how much gravitational energy the sun has, it turns out. Don't worry about this equation, but basically, if you know the law of gravity, you can calculate how much energy can be stored just gravitationally in a ball that has some mass. And it turns out that if you do that, the sun has about 10 to the 41 calories of energy. Right? 10 to the 40 joules of energy. And he estimated the age of the sun using kind of an interesting estimate. What he said was, look, I know how much energy is coming out per second, because I can measure that. You know, you can put a detector up and just count how much energy is hitting your detector per unit area on Earth, and you know how far away we are from the sun. You can figure out how much energy is spitting out. Okay? Basically multiply it by 2 billion, and you get all the energy that's coming out. And he says, I know how much energy it has. So if you know how much energy is coming out per second, and you know how much energy it has, you can get a rough estimate of how long it's going to take to run out. And that's not a bad guess for how old it is. Okay? So for example, you walk into a room, you see a bucket, and it's got a hole in it, and water's just draining out of the bucket. If you measure how fast the water's coming out of the bucket, you can have a pretty good guess of when whoever came along punched a hole in that bucket. Okay, it wasn't 4 years ago. You know, it was like maybe 3 minutes ago, depending on how fast the water's coming out of the bucket. You see what I mean? So this is kind of his estimate. He's got this big bucket of energy, it's leaking energy, he knows how much energy it's got, he uses that to estimate the age of the sun. And when he does this, he gets 30 million years. So he says, look, the sun is like 30 million years old. That means the Earth can't be much older than, you know, it's probably about 30 million years. People get roughly what he's doing? Now, in 1859, his contemporary Charles Darwin wrote this book called The Origin of Species. Now, he was concerned with how old the Earth was, right? Because he wondered whether there could be enough time by natural selection to give rise to all the different kinds of species that we see. And in fact, in his book, he had made an estimate of how old the Earth was. And he did this by looking at erosion, how long it takes for some erosion to happen, and at that pace of erosion, how old can this canyon be? Okay. And by doing this, he got an age for the Earth of greater than 300 million years. And he concluded that, therefore, this is long enough for natural selection to produce all the different species that he was worried about. Any questions about this? Now you've got Lord Kelvin. You know, he's like the most famous, revered physicist alive. Turns out this book that Darwin wrote got some attention. People noticed it. Kelvin looks at this and says, these biologists don't know anything. This is stupid. I, physicists, have calculated this number. There's no way the Earth can be 300 million years old. And he attacked Darwin explicitly and openly. Okay? And in fact, Darwin was really disturbed by this argument. And if you look, he took this discussion out of the next edition. He just took it out. Because he didn't know, you know, what can I possibly do? How can I explain that the Earth could be this old, given this great argument from Kelvin on the age of the sun? Now we now know that Darwin is right. The Earth is actually about 4.6 billion years old. We have lots of different reasons why we think that that's true. And Kelvin was wrong. Who knows why? Why was Kelvin wrong? What did Kelvin do wrong? Let me see if anyone else raised their hand, because you guys have both answered. Anybody else? We've got two. Okay, we got somebody else. All right.
Did he not take into account that the sun's still producing it?
Did he not take into account the sun's still producing energy? He did. Okay, that's not quite it. You're getting there. All right. Okay. You want to take a shot? Okay, you take a shot.
When Kelvin was measuring energy, I guess he didn't know the size of the sun, he just knew how much energy was left.
Okay, is it because he didn't know the size of the sun? Maybe he didn't know like how much energy was left? No, it's not that. Yeah? Yeah?
Because the energy of the sun doesn't come from gravitation.
Yes, because the energy of the sun does not come from gravitation. Who knows, where does the energy of the sun come from? Yeah? Nuclear fusion. Okay. Lord Kelvin did not know the equation, the first equation that was mentioned in this class today. Okay? He didn't know this equation. This is the equation that tells us if you could somehow figure out how to convert small amounts of mass into energy, you could produce a lot of energy. And that's what nuclear fusion is doing, turns out. Okay? So it was Einstein in 1905 who contributed the first key insight to what powers the sun. Okay? He figured out that a little bit of mass could in principle be converted into a whole lot of energy. Specifically, if you have some amount of mass m, and you multiply it by the speed of light squared, that's how much energy you're talking about. And the speed of light's a really big number. So eventually, pretty soon then, people figured out that 4 hydrogen atoms, this is sort of a detail, and I'll get into this process a bit more next time, that 4 hydrogen atoms, if you compare that to 1 helium atom, the 4 hydrogen atoms are heavier. And why does this matter? A helium atom in the nucleus has 2 protons and 2 neutrons. So in principle, if you can take 4 helium nuclei, or hydrogen nuclei, and fuse them together in some chain of processes to create a helium nucleus, you've given up mass to do that, and there's energy associated with that lost mass. And so it's this process that powers the sun, it turns out. And at the core of the sun is mostly hydrogen, but basically what it's doing is it's fusing hydrogen into helium, making helium, creating brand new helium. And this helium, this energy, the mass difference between hydrogen and helium, is what gives rise to energy. It's that energy that's powering the sun. And that energy is much, much more efficient. It's a much more efficient source of energy than gravitational energy. So basically the bucket, I gave you the analogy that the bucket, the leaking bucket, it turns out the bucket was much, much bigger than Kelvin realized. So therefore it had been draining a lot longer than he realized. Okay. So this process of nuclear fusion, which again I'll talk about more in detail next time, in the sun is the process of basically you take 4 protons and turn those into, again, a series of reactions, 2 protons and 2 neutrons in the nucleus of a helium atom. And in fact, when you do this, you lose energy, you lose mass, and gain energy. Now this is a little bit weird, it turns out, because actually neutrons are heavier than protons. They're more massive than protons. So it's actually in making this nucleus that you lose mass. It has to do with the binding energy of the nucleus. But it's this mass difference that you stick into the E equals mc squared formula to get how much energy you're producing. Now this concept, this E equals mc squared concept, let me just talk to you about it just a little bit. So basically mass had been around for a long time. Since Newton, people had known about mass, right? Mass is the thing that kind of resists acceleration when you apply a force on an object. It's how much stuff there is that resists motion in some sense. Resists acceleration. So it's how much matter a system has, okay, we know that. And in fact, there is this law of conservation of mass, okay? So you can take a box of anything, and you can do anything you want to with the stuff in the box. It's hard to change the mass of the stuff in the box. Even if you take a log and you burn it, if you collect all the ash and all the gases that come out, if you weigh all that stuff before you burn the log and after, it will basically weigh the same. So it's hard to get rid of mass. Okay, you're just moving it around. And it's the same thing with energy. There's a conservation of energy law that we talked about before. Burning of coal gets transmitted into sort of moving a train, modulo losses due to heat and stuff like that, right? But it turns out that it's not just mass and energy independently that are conserved. What we now believe is conserved is something called mass energy. It's mass and energy because you can actually convert this into this and vice versa, it turns out. It turns out you can actually create new matter from energy as well. 2 lectures from now, not today, I'm going to give a whole lecture on Einstein. But just for sort of point of information, let you know, Einstein actually derived E equals mc squared starting with 2 very simple postulates. One was that the laws of physics take the same form in all uniformly moving reference frames. So that means if you're on a train and the train's moving at constant speed and you do a physics experiment, you'll get the same answer there as you would if you were just on the ground and it wasn't moving. Okay? And the second one was that in any inertial frame, in any constantly moving frame in your laboratory, the velocity of light is the same, whether or not the light is emitted by a body at rest or a body in uniform motion. I'll talk a bit about this next time, but that's a weird assumption. It says the speed of light is special, that if you're moving fast and you throw a ball, the ball will appear to be going even faster, right? If you're in a moving car and I stick my arm out the window and throw the ball, okay, I'm going 60 miles an hour, and to me, I throw the ball at 10 miles an hour. You know, when it hits you in the head, it's going to hit you at 70 miles an hour if you're sitting still. You don't want to get hit with that ball, right? But Einstein said if I stuck my arm out the window and turned a flashlight on, the flashlight would be coming out at the same speed as it would if I were on the ground and not moving with the car. So you don't add that 60 miles an hour to the light. It turns out with that and that alone, all kinds of stuff comes out, all kinds of craziness comes out because of that. And one of the things that comes out is E equals mc squared. And again, I'll talk more about this next time. Let me just give you, I want to close with just giving you an example of how much energy we're talking about. Now, C, like I said, is a very big number. It's 300,000 kilometers per second. So you can take a small amount of mass and multiply by a big, big thing, and in principle, there's a lot of energy locked in. So I can ask this question. How much energy is locked into, in terms of E equals mc squared energy, how much energy is locked into 1 gram of anything? If you can convert that mass into pure energy. Okay, so if you had some kind of nuclear fusion power plant that could convert mass into energy, and you converted 1 gram of that stuff into pure energy, how much energy are we talking about? Well, E equals mc squared, you put m in, that's 1 gram. You put c in, it's 3 times 10 to the 5 kilometers per second, and you square it. If you multiply all that stuff out, you get 9 times 10 to the 10 grams times kilometers squared per second squared. Okay? And it turns out that that is equal to 9 times 10 to the 13 joules. That's a very, very big amount of energy. 9 times 10 to the 13 joules. And more generally, you can now rewrite E equals mc squared this way. So if I have a mass in grams, I just multiply it by 9 times 10 to the 13 joules, and that's how much energy we're talking about if we convert it into pure energy. So if I have 100 grams, I just stick 100 in here, and then I have 9 times 10 to the 15 joules. Just scales. So in some sense, this equation right here in yellow is E equals mc squared. It's written in a different way. So what this means is, right, if we could figure out how to do fusion, diffuse energy, we could create a lot of energy. It turns out there's another type of nuclear energy that also relies on the same principle, and that's called fission. So that's, you take really heavy atomic nuclei, like uranium, and you break it up. And when you break up a really heavy nucleus, it turns out you can lose energy that way compared to the nuclei that it breaks into. And that also allows you to create energy. And that's how nuclear power plants work. That's what nuclear power plants are doing. Fusion energy is a bit better because the waste products are a lot safer. In principle, if we could get it to work, if we could create mini suns on Earth, then we'd have like a sun, which is producing all this energy really efficiently, which would be great. Turns out that that's probably not going to happen anytime super soon. But let me give you an example of then using this equation. How much mass energy is locked up in a Big Mac? Let's go back to the Big Mac. So you've got a Big Mac. Big Mac weighs about 100 grams, let's say. And let me use this equation that I just derived to figure out what the total energy in a Big Mac is. So I could just take it and just turn all of its mass into energy, rather than extract its chemical energy by eating it. So if you do that, you find that it's 9 times 10 to the 15 joules. Now in terms of food calories, there's about a factor of 100 or so difference. In terms of food calories, it's 4 times 10 to the 3 joules. Sorry, 1 food calorie is 4 times 10 to the 3 joules, so that means the energy of a Big Mac is 10 to the 12 food calories. That is, if you could take that mass energy and convert it entirely into food calories that could somehow be used by people, that's 2 times 10 to the 12 of them. That's enough energy, enough caloric energy, to allow the population of Chicago to live for a year. Just in one Big Mac. If you could convert its energy, its mass, into pure energy, and then somehow inject it into people, right, and allow them to. Right. It's a crazy idea, but just a sense of like, you know, in principle, converting mass into energy is an amazing source of energy. And it's this idea that it was this, you know, missing link that Kelvin didn't have, and it's why he got this argument with Darwin wrong, and in the long run has embarrassed himself. So that now we can kind of mock him. Okay, we're done. I hope you go to the observatory tonight, and if not, I'll see you on Thursday.